Okay, so this is part two of our lecture on molecular orbitals. And in this lecture, we're going to concentrate more on the molecular orbital energy diagrams. We're going to start with H2 with the dihydrogen molecule, and then we'll move to the second row, homonuclear diatomic molecules. So these molecular orbital energy diagrams, this is something you may have run across before uh, in general chemistry or organic chemistry. And here we're going to talk about them perhaps in a bit more depth or a bit more explanation about what is the reasoning behind these diagrams, what they represent in terms of the quantum mechanics of the system. So first of all, let's take a look here. We've got energy along the y-axis here, right? And we start with the the atomic orbitals on either side here, representing with a line segment representing each of the atomic orbitals. So if we're bringing two hydrogen atoms together, then there's going to be a line segment corresponding to each hydrogen atom, and those are on the left-hand side and the right-hand side. And then in the middle, we have line segments for the bonding and anti-bonding orbitals. The bonding orbital here is sigma g 1s, and the anti-bonding orbital is sigma star u 1s. Then so the molecular orbitals go in the middle of this MO energy diagram. And then we use these dotted lines here, these dotted lines, to indicate the atomic orbitals from which those molecular orbitals derive. Then the next thing we do is we include these harpoons or these sort of arrows for the electrons. Each hydrogen atom presumably starts with one electron. They're both bringing one electron to the molecule. And then those electrons end up in this sigma g 1s orbital. So we have our electron occupancy of the atoms that we started with are shown on the left and the right using these harpoons or arrows. And then, of course, where the electrons are for the ground state, or perhaps an excited state if you're talking about an excited state, an excited state electronic configuration. But here we're talking about the ground state. Both of these electrons go into this sigma g orbital, and so we have one sort of up spin electron and one down spin electron. And of course, we know from our work on Slater determinants and on exchange of spin labels that this is an approximate picture, but nevertheless it is a good starting point. It helps to inform our more detailed wave function picture of what these molecular orbitals look like. The other thing that we like to do is, so we like to label the molecular orbitals with the corresponding molecular orbital label, such as sigma g parentheses 1s or sigma star u parentheses 1s. We put the electrons in the orbitals represented by the electrons sort of sitting on the various line segments. Then the other thing that is often included in a more complete molecular orbital energy diagram is to have these sketches here of what the molecular orbitals look like. So in the case of the sigma g 1s, we have this sketch here that indicates a bonding sigma type 1s type orbital. And in the case of the sigma star U, we see this antibonding orbital here. And so reiterating a couple of these rules, I have on the right-hand side of the diagram here, I have a couple of bullet points here. One is that, yeah, the left and the right indicate the atomic orbital energy levels. We see line segments for those. In the middle, we see the MO energy levels. And again, we have these dashed lines to indicate the atomic orbital's relationship to the molecular orbital. Another thing, of course, that we notice from this is we started with 2 atomic orbitals and we end up with 2 molecular orbitals. And this is a general rule. The number of states is conserved when we go from atoms to molecules. So if we have 2 1s atomic orbitals, 1 for each hydrogen atom, then we're going to have 2 corresponding molecular orbitals. Finally, I'd like to note that the bond order can be read off from one of these diagrams relatively simply. We have this, of course, we know that the number of covalent bonds in H2 is 1. And so we say it has a bond order of 1. And we can calculate the bond order for some electronic configuration by counting the number of electrons in bonding orbitals minus the number of electrons in antibonding orbitals, then take that difference and divide it by 2. So in this case, we're going to have the number of electrons in bonding orbitals is n equals 2. The number in antibonding orbitals is 0. And so we have 2 divided by 2 equals 1. The bond order is 1. Now for the H2 plus molecule ion that we discussed previously, the bond order would be 1/2. So it has sort of half of a covalent bond. Now let's move to the second row, homonuclear diatomic molecules. So I'm talking here about constructing potential or possible molecules made from lithium-2, beryllium-2, boron-2, carbon-2, nitrogen-2, oxygen-2, fluorine-2, and neon-2. Of course, these might not actually form molecules, but we sort of let the diagram show us that. So we're going to sketch our MO energy diagram with the various labels of the MOs and the atomic orbitals. And we're also going to sketch each orbital. And we're going to start with an empty diagram, not going to put electrons in it, and then we'll march across the second row. So let's take a look at this. First of all, we put 2p higher than 2s. And because we have 3 degenerate 2p orbitals, we use 3 line segments for each 2p orbital. And again, these are homonuclear, so it's the same nucleus on either side. So presumably the atomic orbitals for 2p on the, say, left atom are the same as the energy level of the 2p orbitals for the right atom. Then in the middle, we set up various line segments indicating the various molecular orbitals in this system. There's this question of which of the bonding orbitals involving 2p is higher in energy. In this particular diagram, we're going to start with sigma g is higher in energy than pi u. And sigma g, that's for sigma g for the 2px orbital. And we'll see that some atoms follow this rule, and then for other atoms, it's actually inverted, where the pi 2p orbital is higher in energy than the sigma 2p orbital. Okay, then above those, the pi u and the sigma g, we have pi star g and sigma star u. I believe always sigma star u is the highest energy orbital for 2p states. The pi star is also antibonding, but at a little bit lower energy. And you notice that the bonding orbitals are lower in energy than the corresponding atomic orbitals. And that makes sense if we consider bonding as being a lower energy or more stable state for this molecule, assuming that the electron configuration, that there are more electrons in bonding orbitals than antibonding orbitals. Okay, then, and again, we have 2p above 2s, and the reason for that is that there is a removal of the degeneracy between 2s and 2p as you move into the second row, and you're actually putting electrons into these orbitals. There's electron-electron repulsion and other effects, spin-orbit coupling, and so on, that move the 2p orbitals above the 2s orbitals. And so our atomic our 2s and 2p orbitals are no longer at the same energy. They're actually split. So for the 2s, we have the lowest energy orbital, which is our bonding orbital, is the sigma g 2s. And then we have this antibonding orbital, sigma star u 2s. And then we've sketched all of the various molecular orbitals, or most of the various molecular orbitals here, in the general vicinity of where those orbitals are, so that you can see that this one corresponds to sigma g 2s, and this one over here corresponds to sigma star u 2s. And then, of course, above that we have this sort of sandwich-looking, meatball sandwich-looking pi u orbital here. And we have our sigma g 2px orbital. So we're assuming that 2px is along the intermolecular axis. So x is our intermolecular axis in our convention here. And of course, in various other books, you may see z as being the molecular axis. But here we've picked x. And then we have pi star g. It's this kind of butterfly-shaped orbital above that, and then sigma star u, which is our highest energy orbital. And as I stated above, 2p is higher in energy than 2s due to various effects involving multiple electrons. Now, as it turns out, the way we drew this diagram here, we have sigma g 2px above pi u 2py 2pz, and that is what we expect for part of this second row. For lithium 2 to nitrogen 2, that's the energy ordering. However, pi u 2py 2pz is higher in energy than sigma 2p x for O2 and F2. It turns out it usually doesn't really seem to affect the bonding properties or even the paramagnetic properties very much of the molecules, the fact that there's this switchover, but I like to include that just for the sake of completeness. Then finally, before we start putting electrons into this diagram, we need to consider that the Hund's bus seat rule applies to this system, meaning that we have various molecular orbitals here where there's a degeneracy, say in the pi u, right? There's going to be two different pi u molecular orbitals. There's the one that's sort of in the page that I've sketched here, and then there's another one that's kind of out of the plane of the page, has a cloud above the page and a cloud below the page. Those two are degenerate, and when we put electrons into those pi u molecular orbitals, we'll need to follow our bus seat rule, meaning that we put one electron in the left line segment and then one electron in the right line segment. And that's, so if you have two electrons, that's where they go. Of course, if you have four electrons, then they're both going to be completely filled. Okay, and I think, yeah, that's it. So let's go ahead and see, is there anything else? Yeah, and let me make clear here, right, where I have 1, 2, or 3 line segments that are sort of at the same energy level, right? Energy is along the y-axis here, is along the vertical. So when I see 2 segments at the same energy, that means there is a degeneracy. And of course, we need to keep track of degeneracies because we're going to be putting in some certain number of electrons, and we need to keep track of how many electrons can go into which orbitals. So you can put 4 electrons into the pi u, and you can only put 2 electrons into, say, sigma g, and so on. And of course, you can put up to 6 electrons in your in each of the in the 2p orbitals for each atom. Okay, let's move on to actually looking at some potential homonuclear diatomic molecules. Let's look first at Li2. It has one electron in each. Oops. It has 1 electron in each 2s orbital, and so it has of course 2 atoms making up the molecule. So it's going to have 2 electrons in sigma g 2s, and it looks like this. Let's scroll up. We start with our electrons in each of the 2s orbitals, and then of course they just sort of fall into this sigma g 2s. And if we look at this, we have 2 electrons in a bonding orbital and no electrons in any antibonding orbitals. And so the bond order is 1. Also, in the lowest energy state of this system, those electrons are going to be spin paired, 1 spin up, 1 spin down. And so there's no net spin for this molecule. And so it is it is a singlet. And it is diamagnetic because it doesn't have any unpaired spins. Now let's consider beryllium-2. Don't want to spend too much time on beryllium-2. Beryllium's pretty toxic. It has, each atom brings 2 2s electrons into the system. And so that's going to be 4 total electrons. So there are going to be 2 electrons, oops, in sigma G, and 2 electrons in sigma star U. So it's going to look like this. We start with 2 electrons on each beryllium atom. That gives us 4 electrons in the system. And so this is our lowest energy electronic configuration for the molecule. All of our spins are paired, so this is a singlet. It's diamagnetic. And the bond order is 0 because there are 2 electrons in a bonding orbital and there are 2 electrons in an antibonding orbital. And so they sort of cancel out the bonding, and you get a net no bonding in this system. So if you bring 2 beryllium atoms together, they won't really tend to stick, right? They're going to be, it will fall apart. That molecule will fall apart pretty easily, except maybe at very cold temperatures, or if there's something holding the 2 atoms in place, like they're in some sort of lattice or something. Now let's move on to boron. Look at diboron. So we looked at dilithium, diberyllium, now diboron. So it's going to be like the previous case. So it's going to be Be2 plus we're going to have 2 additional electrons in a 2p orbital, and there's going to be 2 electrons. The next highest molecular orbital is going to be pi u, 2px, 2py, or sorry, 2p, 2py, 2pz. So scrolling up, we're going to start with electrons in that p orbital. And since there are 2 degenerate levels, according to the bus heat rule, this would be our lowest energy state. And this is going to be a triplet state, right? That can be either spin up or spin down, or some sort of weird linear combination of spin up and spin down. So there are 3 of these states, kind of like in the case of excited helium. So this is a, boron has a bond order of 1. And it's a triplet. And it is paramagnetic. meaning it will interact with a magnetic field, and it will exhibit a sort of Zeeman type effect. Now let's move on from boron to carbon. That's going to have 4 electrons in pi u. So they'll pair up like that. That will be the lowest energy electronic configuration. And this will give us a bond order of 2 and a singlet. And it's thought that C2 is, it's believed to be a component in plasmas, say in a spark gap between carbon electrodes. It's sort of C2 units that are buzzing around in there as being one of the principal species. And so because it looks like it should be a relatively stable molecule, it has a bond order of 2. And so this is known to exist, even though, of course, it's not the sort of typical state of carbon is, say, graphite or diamond, but in the gas phase in a plasma, C2 can exist. Now, if we move on to N2, again, putting 2 more electrons into the system. Now we're going to be moving electrons into sigma G. Oh, and I forgot to put one of our electrons in the last system. Okay, so now we've got, 3 electrons, 1 in each of the 2p orbitals. Then we bring the nitrogen atoms together, forms these molecular orbitals that we represent in the middle here, and we're going to put 6 total electrons into the system. It's going to be a triple bonded singlet state system. And it's going to be diamagnetic. So nitrogen is a very stable molecule. It has a very short bond length, and that's in agreement with our molecular orbital picture. Now for oxygen, we're going to have 2 additional electrons in our pi star G orbital. Those electrons are going to be unpaired. That's going to be the lowest energy state according to this Busseit rule. And you may recall the underlying physical reason for why this kind of electronic configuration, where we put 1 in each orbital, is lower energy. There's a couple of ways of thinking of that. One is that due to the statistical tendency for electrons to avoid one another if they have the same spin, this type of configuration where they both have the same spin is going to put the 2 electrons kind of out of phase of one another, so they tend not to be in the same place at the same time, and that's going to reduce the amount of electron-electron repulsion in the system, thus lowering the total energy of the system. Also, of course, this places one electron in each of two different orthogonal molecular orbitals. So those molecular orbitals occupy different regions in space. And one of them is sort of in the plane and the other one is out of the plane. So that's going to be a lower energy configuration. Of course, it's still a anti-bonding configuration, but the electrons in those orbitals are going to contribute to the overall total energy of the system. And so any molecular orbital that we stabilize is going to reduce the total energy of the system. So that's the lowest energy configuration for O2. O2 has a bond order of 2. And it's a triplet. Singlet O2 does exist. You can prepare it by things like photosensitizers. It is about 1 electron volt higher in energy than O2 triplet. So it's a very reactive species. I mean, oxygen by itself is reactive enough. You give it an extra electron volt of energy, it's going to be very reactive. So that's a reactive oxygen species. But even the triplet, of course, is pretty reactive. For F2, and I neglected to include the electrons on the 2p orbitals for oxygen. So there's oxygen. Then we're going to add 2 more electrons here. That's going to put 2 more electrons here. And we end up with a bond order of 1 and a singlet for F2. And of course for neon, all filled, bond order is 0, and it's a singlet. So neon 2, of course, not going to be a very stable molecule. So we've run through and populated a molecular orbital diagram for the second row homonuclear diatomics. That's the end of this lecture.